Hey everyone, Mr. Newman here. In today's video, we're going to learn about exponential functions. And I just want to tell you, exponential functions get big fast. No, seriously, really, really big, really, really fast. And I want to show you guys that we humans have trouble wrapping our minds around how big and how fast exponential functions get. So I have some examples to show you. Well, first of all, I want to talk about vampires, okay? So you're a little vampire here. Yeah, what do you know about vampires? Well, I know that they aren't real. At least that's what some people say. There are very oddly specific ways to kill them, like garlic, wooden stakes, sunlight, huh? Or maybe sunlight just gives them a sunburn. I don't know. They also must drink human blood. Apparently, that's a thing, right? Again, going back to the aren't real, but okay. And if they bite you, then you turn into a vampire, right? Some stories have that happening, so we're gonna say that happens here. And let's pretend that vampires have to eat one or must bite one human a day. So not eat a human; they just drink the blood, right, of one human a day. So what happens that human? They're going to become a vampire, right? And so my question to you is, how long before the whole world is a vampire? I'm going to let you go ahead and make a guess there. Okay, now that you made your guess, let's do a little math and see what happens. So you have one vampire on, we call it day zero, kind of like patient zero is the first one. On day zero, when nothing else has happened, we have just one vampire, right? Well, that one vampire goes and drinks the blood of a human, and the next day, well, what's going to happen? Now there's another vampire, right? So that other vampire, then day one, we have two vampires, right? Now, on the next day, each of those vampires has to drink the blood of another human. So we're not going to get one more vampire, we're going to get two more vampires on the following day. So there come the two vampires because each of them needed to drink blood, and there's two humans, so there's two new humans. So on day two, there are four vampires. Well, how many are there going to be on day three? Well, each of the four vampires now needs to drink blood, so there's now going to be 8. You notice we're doubling each time, right? So on day 3, there's 8. On day 4, there's 16. And oh my, there are just so many vampires. They're coming and they just can't stop, right? So notice on day 6, we already have 64 vampires, which is kind of crazy, but it gets crazier, okay? One thing I want you to notice as we get into the math here, look at this. Another way to write these numbers, you can write 4 as 2 times 2, right? And you can write 8 as 2 times 2 times 2, or 16 as 2 times 2 times 2 times 2. So there's a faster way to write this, right? Like we can write this 2 times 2 times 2 times 2 times 2, that's just 2 to the 5th. Remember, mathematicians are lazy, so writing a little number up high to show how many times you multiply them together, we know that, right? That's called an exponent. And so you notice a pattern now. Do you see the exponents, how the exponents are related to the days? If so, you're right. They are the same, right? And now, since they're the same, we can go back up here. What should go up here? Well, 2 to the 0, which, oh yeah, 2 to the 0 is 1, because anything to the 0 power is 1, and there's one vampire. So that kind of makes sense here. So what that means is that we can answer our question, how long before the whole world is a vampire? Well, if it's 2 to the day number, our equation is just going to be 2 to the x. You see this over here? That means on day 1 here, let me make a table out of this. On day 0, we get 1 vampire. On day 1, we get 2. On day 2, we get 4, 8. And look, there's our exact same table where x is the number of days and y is the number of vampires, or f of x is the number of vampires. So to answer our question of how long before the whole world is a vampire, we need to know the world population. Well, did you know that there's a world population clock online? You can just Google it, what's the world population, and you can find this. This blows some students' minds. Look at this. Births today. There are this many births in the world today. And yeah, those numbers are going up because babies are getting born somewhere in the world that fast. Now, it's an estimation, it's approximation, but that's about the rate that it's happening, which is kind of crazy, right? There's also deaths are going up that fast too, which is also morbid, but yeah, the population, the births are growing faster than the deaths, so the world population is just getting bigger all the time, right? So I'm going to round it, say let's say 7.8 million, okay? 780000000. Let's see here. I'm going to type this into y here because that's the population or the number of vampires. So y equals 7.8. Sorry, did I say million? I meant billion. This is million here. This is billion. So I need 1, 2, 1, 2, 3, 1, 2, 3. Great. Now the other problem is this is way off the graph, right? Let's zoom into our graph here. I'm just going to press a few more. So after 10 days is 1,000. And let's do this now. Whoops, zoom in there. I'm going to zoom all the way up to where I'm going to zoom out until I can see this. Actually, let's do this. I can click this button, and on the y-axis, I can make this go up to 10 billion. There we go. Do you see it right there? So, when the number of vampires is 7.8 billion, that will be on day 33. It only takes 33 days to get to, or 32, actually the afternoon of the 32nd day. It only takes 32 days to get to the 7.8 billion. So what does that mean? That means if there's a vampire somewhere in the world and they really had to eat one a day, remember they can turn into bats and flies, so they can go wherever they want, we would know about it because the whole world would be infected in a month. So that's why I'm pretty convinced that vampires aren't real. Otherwise, we'd know about it. Now, there are a few crazy things we can go here. Let's ask this question. How long before the whole world is a vampire? Well, how long before half of the world is a vampire? What do you think that would be? Go ahead and make a guess. Remember, the whole world becomes a vampire 32.8 days. Okay, now that you have your guess, I'm going to show you how to do this. So let's copy and paste this. And I'm going to let Desmos do the math for me. Divide by 2. That means this is half of the world's population, right? It's 3.9 billion. And what day is that? Oh, yeah, one day before. Which is crazy that like half the world becomes a vampire on the last day, which makes a little bit of sense because remember it's doubling. So go back one day, it'd be half that amount, but it still is crazy. Like I said, exponential functions, they get big fast. Let me tell you another story, okay? This is this Chinese emperor and rice chessboard story. So in ancient China, there was an emperor, and the emperor, let's say, had a daughter who was in grave danger, and a poor farmer went and saved the daughter. Yay! So the emperor said, I will give you whatever you want. You know, half the kingdom can be yours. And so the farmer, he thought, and he said, all I want is a chessboard where you put 1 grain of rice on the first square, 2 grains of rice on the second square, 4 grains of rice on the third square, 8 grains of rice on the fifth square. So you're just doubling the rice. So you see, 1 grain of rice, then 2, then 4, then 8. And the emperor is going, that's all you want? Just some rice on a chessboard? Well, what the emperor didn't know, and the farmer did, I guess, was his math. Because how many squares are there on a chessboard? Well, 8 and 8 means 64. There's 64 squares on a chessboard. And if you double something 64 times, there is a tremendous amount. That is a giant number. I'll just hop over here and let's just type in 2 to the 64. This uses scientific notation. Remember, it's 19 is how many times you multiply by 10. So it's really like 1, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Oops, 18, 19. There we go. And yeah, that's the number, which is crazy. That's just on the last one. And so let's, I also did a little math to figure out what this means. It can be written like this, okay? 18, whatever that is, bajillion, trillion? I don't know. And let's do a little math. So a grain of rice is about 0.2 inches long. If you convert it to feet and divide it by miles, and what you do is, it means that that much rice is this many miles right here. 60, I think that's trillion. Yeah, 60 trillion miles. So if you put the rice end to end, it goes all the way to the nearest star, Alpha Centauri, other than our sun. It goes all the way there and back, which is insane because we can't even picture how far away Alpha Centauri is. Our minds can't handle that. So exponential functions get big fast. Here's another situation I want to give you. Let's say you're offered a job which lasts for 7 weeks and you get to choose your salary, okay? You get to pick which of these you want. You could either get $100 the first day, $200 on the second day, $300 on the third day, and so on, and you're paid $100 more each day, which is pretty good because at the end of 7 weeks, you're going to make 7 times 7 or 49 times 100. That's $4,900. That's pretty good. Or you can get 1 cent on the first day, 2 cents on the second day, and 4 cents on the third day, and keep going until each day is just doubling that, right? But you're only starting at 1 cent. Which of these options do you think is better? Well, now that you made a decision, let's find out. So what I'm going to do is I'm going to go over to Desmos, and I went ahead and made the two functions here. You see this? So you have the first day is 100, second day is 200, third day is 300. This is the, we call that a linear growth, okay? I keep doing that. I can zoom in here. You can look at the graph and see which one is better, right? The black one is clearly better, at least in the beginning, right? That's the 100 more each day. That's really, really good, okay? So, well, let's skip on down. Let's see here. At the end of 1 week, that's $700. At the end of 1 week for green, that's just 64 cents. Huh. At the end of 2 weeks, that's 2 times 7, or 14. That's $1,400. Okay, let's zoom into that. And here at the end of 2 weeks, that's $81. Still not even as much as the first day. Let's get to the third week. $2,100. $10,000. What? Let's go to the end of the fourth week. 4 times 7. That's 28 days later. It's going to give you $2,800. And 4 times 7 is what? What is this? $1.3 million? Let's zoom in to this one and see. Oh, so this is the exponential curve. See how steep it is? We can't even see. Oh, we have to zoom way out there. And look at that. We have to zoom way out here. I'm going to click this button and zoom in. Look at that. Now, one of the things I have to caution you about, I zoomed in to this point way out here. Every other point just looks like it's basically at zero because compared to $1 million, $2,000 is basically zero. If you ask for $2,000 from a millionaire and they're like really nice, that's like giving a penny away, you know? So that's crazy, but let's go all the way up to 7, okay? So at the end of 7 weeks, I said that was $4,900. At the end of 7 weeks here, that is more money than the entire United States GDP. Like all the money in the US, like maybe in the world, right? This number is tremendous, okay? Yeah, there's not enough money in the world for that. So exponential functions get big fast. If you're ever offered one of these, take it, okay? The person will realize very quickly they can't pay you that much. Another thing I want to show you is that we have no idea about big numbers, right? About big numbers, big numbers. There we go, big numbers. I want to show you with the number line, okay? So let's say this number line right here. All right, we got a number line. And on the left of the number line is the number 0. And all the way to the right is a million. Whoopsies, 1 million, not that, whatever that was. 1 million. There we go. Okay, so my question for you is, where is the number 1,000? Where on here is 1,000? Go ahead and put your finger on it maybe, or make a guess, make an approximation. Where would 1,000 be on here? And now what I want to do is I want to give you some options. Okay, let me change this. It's just bothering me just a little bit. There we go. Still is a 0 to 1 million, right? And let's say, do you think 1,000 would be to the left of A, between A and B, between B and C, or to the right of C? Okay, which section do you think 1,000 falls into? Okay, go ahead and make a guess. All right, so now that you made your guess, I want to show you guys. Actually, 1,000 is right here. I have to draw a line. And in fact, the line that I'm drawing, yeah, this is going to be bad. Oops. Let's see, I wish there was a way to zoom in. There's not, is there? There we go, zoom in. Yep, nope, this is too far. Let me move this over here. You know what, it's still too big. I can't make it smaller. This line right here is too thick, okay? 1,000, I'll make it yellow so you can see it. 1,000 is smaller than that little tiny black edge on that side right there, okay? Because it's 1/1000th of a million, and each of these dots, I counted the dots, there are about 100 of these dots. So that first dot there is roughly 10,000. So 1/10 of that is 1,000. Very, 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 very tiny. Like you can't even see it on this scale, okay? I also have this neat video. Whoops. Let's go back to here. I'll link this video in the play posit so you can click on that and see. But that's a cool video where it shows you how rich some people are, and you can see how little money even rich people have compared to the really, really rich people, okay? Pretty neat. So yeah, exponential functions get big fast, and we can't even wrap our minds around them. There's some other situations that use exponential growth. It's all around us. Money grows exponentially. That's why people who can invest in bonds and stocks get richer even faster. World population, of course, grows exponentially. There's a neat zooming app. I'll link that as well in the video. Bacteria grows exponentially. In fact, there was a neat situation in 2010. There was a giant oil spill, I think off the coast of Mexico it was, in 2010, and it was all over the news. They're saying there's so much oil, this is terrible, we're never going to be able to clean this up, it'll hurt the wildlife. Well, what some scientists discovered, or what they used rather, was they used a bacteria that ate the oil and decomposed naturally. And what's incredible is you didn't have to put very much bacteria. The bacteria multiplied and grew and grew and grew. The more oil it ate, the more it multiplied and split. Before long, it was able to eat all the oil up, even though it was a tremendous amount of oil. They didn't need to collect a ton of bacteria because the bacteria grew exponentially. And then the bacteria, of course, just died and decomposed in the ocean. And it was a very, very good solution for a terrible mistake. Diseases also grow exponentially. So there's the 2014 Ebola crisis, but right now, the more significant thing is coronavirus, as you guys are aware of and have already done a project on. It grows exponentially. And on your project, I got a few people asking, Mr. Newman, this doesn't seem right. This number is too big. Oh no, it's right. Exponential functions grow big fast. Avalanches and rock slides actually grow exponentially. It just starts from a tiny snowball falling, and then there can be very dangerous amounts of snow or rocks falling down the side of a mountain. Nuclear chain reactions. So this is actually an example of that. What happens, that you guys have probably heard of the nuclear bomb, is the largest bomb available to humans right now. Well, that bomb starts from just a tiny, tiny few pieces of atoms that then split and hit other atoms, and they split and hit other atoms until soon a tremendous amount of energy is released because of the exponential growth. If it wasn't exponential, it wouldn't be as much energy. Feedback in microphones, when you hear the microphones get real loud and spiked, that's exponential growth as well. And pyramid schemes, which are legal, are also exponential growth. You can look up those, but it's they're not realistic, and people that try them or are fooled into them just don't know what they're doing. Okay, Moore's law is the last thing I want to talk about. It's this really neat idea that over time, you see in the 1900s all the way up to 2000s, the idea of the calculations per second, and you now know them as computers. Back then in 1900s, they weren't computers. They were things called analytical engines and tabulators. But computers now are getting faster and faster, and they actually double roughly every 1.5 years. They get about twice as fast every 1.5 years. And so what does that mean? That kind of means computers also are going to cost, like the same computer is going to cost half as much every 1.5 years. So going forwards means getting cheaper. And so I'm going to ask a question. My computer is 6 years old and cost $1,000 when I bought it. How much is it worth now? And the other thing is going backwards. Let's pretend you have an iPhone X that costs $1,000. How much would the same technology be worth, say, 12 years ago? And these numbers might blow your mind. So let's tackle the computer first. So I got a 6-year-old computer. It's actually a little older now, but I picked 6 because that's a nice even number as far as being divisible by 1.5. And that means if you go back a year and a half going forward, a year and a half from now, it's going to be half as expensive. It's going to like the same one. So a year and a half after I bought it, the same components you could buy for $500 instead of buying $1,000, right? Oh well, lost a bunch of money. whatever. Well, to keep going forward, that means 6 years later, after I buy this $1,000 computer, you can get the same amount of computing technology for only $62.50, roughly. Okay, which is crazy, which makes me not want to buy any computers because they just get nicer and nicer, the new computers do, and so old computers just get cheaper and cheaper. It kind of stinks, right? But I guess, man, we have to live with computers these days, so that's why I would advise buying something cheaper so its price only decreases by a fraction of that amount. If you go forwards, though, let's say this computer that was worth $1,000, 12 years later, guess how much it's worth? The same technology is less than $4, which is incredible how much computer technology has increased and grown. Now, let's go backwards. This is a more exciting one. So that means if computers are getting twice as good every 1.5 years, that means if you go back 1.5 years, then the same computer is going to be twice as expensive. It's going to cost twice as much. So, for example, an iPhone X, I know the new ones out, that cost $1,000. If you go back 1.5 years, that same technology, if you had that, which of course it wasn't available yet, but if you had exactly that same technology, it'd be worth $2,000. If you go back another 1.5 years, that's worth $4,000. So if you keep going back and the price keeps doubling, which is true, that's the way it works, that means 6 years ago, that iPhone that was worth $1,000 would have been worth $16,000, which is true. If you had an iPhone with all the bells and whistles that it has now, the computing power it has now, and went back 6 years ago, people would have paid easily $16,000 for that iPhone. But let's keep going backwards in time because it gets even crazier. If you keep doubling, 12 years ago, the iPhone that you have now, if you have an iPhone or any kind of phone that's worth about $1,000, go back 12 years ago, it would have been worth $250,000, which is just insane. So exponential functions grow big, fast. Thank you guys very much for watching, and I hope you enjoyed this video.